from the very beginning that there will be nothing about free boundary at all in my talk. In fact, this will be boundary-free problem because everything will be considered on Rn or R3 without boundaries. On the other hand, this is what we believe an interesting set of problems, which is relatively little studied, and there are plenty of open questions here, which possibly lead to free boundaries and other standard questions in elliptic theory. So this is our starting point. This is not Choquard-Type equation yet, but our starting point in motivation. This is what we call Schrödinger-Newton systems. The terminology, the model itself comes from several different models in physics, and terminology is unstable, but we should come up with some certain names. So this is what we call Schrödinger-Newton system. And here in the first equation, you see standard stationary Schrödinger equation with the external potential V, particle described by probability density U, and an additional potential W, which is in fact sourced by a gravitational force of a particle itself.
So it's W multiplied by U. W multiplied by U.
Yes. Yeah, W multiplied. Yeah, W multiplied by U. So if you look here, this looks like a still linear Schrödinger equation with potential V corrected by W, but of course W non-linearly coupled with U itself. And this includes in all these physical models, at least in last three physical models, this contains an idea of some self-gravitation. So particle interacts with a gravitational field generated by itself. This is a model of so-called polarons, 54 Choquard electron trapped in its own hole, and more recently Penrose is a model of self-gravitating particle. Much earlier, this is of course Hartree equation, where the same type of model describes many electron systems, an approximation with system with a very large number of particles. But for us, it's more convenient the point of view of self-gravitation. At least for me, it's something easier to grasp and to understand. And this is just the starting point, and this is of course not a proper system because we can just resolve the second equation with respect to W, just to invert the Laplacian, what I will do here, and we will get a non-local convolution term, and then we substitute it in the first equation. And we update what we call non-local Choquard equation. So for Schrödinger-Newton, we refer this to Schrödinger-Newton system, and Choquard we refer to a single equation when system converted into a single equation. And this equation is variational, and this is associated energy. Here, let me emphasize that coefficient gamma, so after rescaling all physical constant, we can end up with one single coefficient gamma, which is positive, and this corresponds to attractive non-local interaction. So particle attracts itself. There is a large body of literature on so-called Schrödinger-Poisson systems. This is very similar system, but where the sign is different, where particle is repulsive, it anti-attract itself. So in this equation, the gamma would be negative, and mathematically this is a very different type of equation. Not very different, but quite different type of equation. So this is a Choquard equation, and we called it Choquard because this is how Lipp called it in the paper of '77, and that was our original motivation to look at this, one of the original motivations to look at this problem. So Choquard actually never published. Choquard is more or less a physicist, and he never published any paper until very recently on Choquard equation. So first paper on the equation where he called Choquard was published by Lipp. But Choquard proposed this model in one of the physical congress, and Lipp in '77 proved the existence of unique positive radial ground state solution for this equation, which belongs to Sobolev space H1 and which has monotone decreasing and has exponential decay. Ground state was obtained as a rescaled minimizer of mass-constrained minimization problems.
So it's unique in the class of radial.
It's unique, yeah. It's unique, and there is, yes, that's correct. There is obvious translation symmetry, so everything is invariant with respect to translation. So it's unique radial ground state solution. And Lipp obtained it as a mass-constrained minimization, so it constrained the mass m and consider minimizing this energy. Let me emphasize this energy is non-convex. So the problem of minimization is not so obvious, but nevertheless there is a minimizer for this regime, for this set of parameters. Later, Leons looked at the same model, and then Penrose and his group in Oxford, when they come up with a self-gravitating particle model, they, I believe, totally independently, I believe they were not aware of Lip's work. They rediscovered the same result using ODE, or rather integral ODE techniques, because of course it's not, even in radial settings, this is not reduced to an ODE, this is integral ODE, which contains non-local term. So this is Penrose 98. And that was our original motivation for looking at the problem. And we wanted to look at a more general set of equations, what we call Choquard-Type equation. So here we have a more general potential V, external potential V. And instead of inverse Laplacian, so here in the Lip problem, this convolution with x minus 1 is of course inverse Laplacian. We have here arbitrary Riesz potential, so this is inverse of fractional Laplacian of order up to n, and we have more general powers p and q, which for most they will be restricted later to variational case, but this is our starting point. P here any positive number, and Q any real number, which a priori at the very beginning could be even negative. Later on it will become positive, and again restricted to a certain range. So this could be, again, from the point of a system, this could be seen as a half fractional system, half fractional in the sense that second equation is a fractional Laplacian, but fractional Laplacian not of order less than 1, but of order less than n over 2 here in this setting.
So this doesn't include the former thing?
No, it does. It does.
N is 1 there. It was n is 1, alpha is...
No, if you take alpha equals 2 and dimension 3, you get precisely...
n is
dimension. And now any dimension. If you take n equals 3, alpha equals 2, inverse Laplacian, this is the previous thing. And in the physical models, at least there is a question how relevant this to physical models. But for instance, at least the case when we have alpha equal 1, I know some models where alpha equal 1. So here you have half Laplacian root of the Laplacian in the second equation. So this is our starting point, and this is what we call Choquard-Type equation. So a couple of comments. First of all, formally, when alpha goes to 0, of course, Riesz potential with a normalization, and Riesz kernel, we have this normalizing factor A alpha. So with this normalization, Riesz potential goes to delta function in certain sense of, at least formally, I'm not making any claim here, but formally when alpha goes to 0, we will study the local Schrödinger, nonlinear Schrödinger equation. And our Choquard equation is variational if and only if q equals to p minus 1. So power p inside the convolution and outside the convolution should be equal to p. This is the only variational case. When p is bigger than 0, so total power is p plus q here, p plus q here. So when p is bigger than 1, the problem is superlinear, super quadratic. Rather, the equation is superlinear, and the energy is super quadratic. When p is less than 1, the energy is subquadratic. And everybody who worked on semilinear equations knows that those are two very different cases. They treated differently. The main importance of this, when p is bigger than 1, then the energy is unbounded below, is essentially non-convex and unbounded below. When energy p is less than 1, the energy is might be bounded below and coercive under some conditions, at least. So these are some comments. And in my talk, I will cover 3 rather different topics. So first part of my talk will be about Liouville's theorems, and I will comment very soon what Liouville's theorems are, because it's not quite clear. The second part will be existence of ground states in the spirit of Lip's result, and third part will be existence of semi-classical states when we have a small parameter in front of the Laplacian in the convolution term, at least if I have, this is a plan, if I have enough time to reach to the third part. So first of all, Liouville's theorems, and I will start with the local prototype. So I will remind what we call Liouville's theorem by looking at the local equation. And this is a classical, not very difficult to prove result, which goes back to Serians in the early 70s and then was studied by Gides and Sprague in the 80s, Brizis-Cabret 98, and so on and so forth. And the basic result in this body of work is that we look at the equation in exterior of a ball, radius is arbitrary large rho, and this equation has a positive super solution if and only if the power q here is sufficiently large, greater than this critical number, which is often called Serine critical exponent. When q is less or equal than this number, when q is greater than this number, the problem has a super solution which has this decay, which has precisely the decay of the green function. Several comments. First of all, we don't fix any boundary values here, so it's not it's a problem without any boundary values, and I'm talking about class of all positive super solutions. So it's a very large set of functions. There are lots of super solutions among them. But this super solution, this set is non-empty if and only if q is large enough. And this, in a way, minimal super solution in this class has precisely the decay lower bound on the decay of the green function. That's why it's only lower bound. Of course, there cannot be upper bound because there are super solutions of different growth amongst all super solutions. But minimal super solution has precisely green function growth. So this is our local prototype, and this is the result. I will describe the results for the Choquard using what we call Liouville map. So I will comment on what happens here. This is power p in my equation. This is power q in my equation. And we take alpha greater or equal than n minus 2. The significance of this, you can think of, very vaguely speaking, you can think as a total order of the equation is alpha plus 2. So this corresponds to the case of total order of the equation is greater or equal than n. And then blue region is non-existence, where we have no super solutions, and white region is existence, when there are some super solutions. So there is no super solutions anywhere here, and there are super solutions above these lines, and they decay exactly the minimal possible decay. Admissible decay is precisely the green function of the Laplace. This line, if you look at the local equation, this line is roughly what corresponds to the Serine equation, to the Serine critical exponent from the previous slide. And these two lines, they're somehow new and they're specific to Choquard. This picture is not too complex. More complex case we have when alpha is not very large, so when the total power in the equation is strictly less than n. And then again, we have non-existence below critical lines. Critical lines always exist included in the non-existence, and this is something which is quite delicate to prove. Here above the red line, we have green function decay. Here between the red line and critical non-existence line, we still have super solutions, but the decay of super solutions is no longer governed by the green function. It's somehow governed by the green function, by alpha, and by power q here. But it doesn't see the power p, so it becomes to sense the nonlinear nature of the equation. You ask me what happens here on the red line and why the red line is red. Here we have very complex decay structure, which is somehow transient between green function and this polynomial decay, and involves various logarithmic corrections, which are quite delicate to describe. This asymptotics, you may wonder why we are so specific about this asymptotic. This asymptotic will be essential for semi-classical solutions, which I hope to have time to speak at the end. So asymptotics are important. Just a few words how we prove this. So we prove this using what we call non-local positivity principle. This is a class of integral estimates on the distribution of super solutions of our equations that satisfies this sort of integral. It's not identity, it's inequality, because we talk about super solutions. Here phi is a test function which should be chosen carefully, and u our solution. This term is local because phi usually would have a small support on a narrow annulus. This term reflects the contribution of non-local part and altogether allows us to produce various, depending on the choice of phi, various upper and lower bounds on the super solutions, and combined with some standard estimates of harmonic functions. This is used to produce all the results on the previous two Liouville maps, but I should say this is a long work because there are lots of different cases to be considered. But all the results they extracted just from this unique non-local positivity principle, plus harmonic functions estimates for the Laplace. Now, this can be, this is what we call free Laplace, and there was no potential here in the equation. But now, what happens if we add potential? And here there are two cases to consider, what we call fast decay potential. Fast decay is those potential which decay faster than inverse square, and the results are exactly the same as for the free Laplacian. So this is weak perturbation which doesn't affect anything what I said before. Hardy-type potentials is potentials which precisely inverse square with a constant which is less than critical Hardy constant. The results are essentially the same. All pictures look the same, but parameters start to depend on the value of the constant mu, and all critical lines start to depend on the value of constant mu. And if constant mu is large, then there is no positive super solutions, in fact, for the linear part in the equation, and hence for the nonlinear equation. But the all solutions I'm talking about, I didn't mention that we assume that we're looking at positive, not negative or positive solutions. So when I say solution, it's positive solution. So these are Liouville theorems and fast decay or Hardy potential. Slow decay potential, potentials which decay slower than inverse square. And here we have, again, this type of Liouville map, non-existence below this line, and exponential decay above this line. More complex situation in this case where power gamma contained in this range, and this in particular includes the case when gamma is 0, which is a classical physical case of leap. And then we have exponential decay when power q is bigger than 1, and we have polynomial decay, which was very unexpected when power q is less than 1. You ask me, this dotted green line, this is variational diagonal. Those are values when q equals p minus 1 when equation is variational. On the red line, we have complex transitional effect when we have some transition between exponential and polynomial decay of the ground state. You ask me where the physical case is. It's precisely here at this point. And from this point of view, we see that it precisely fits in the transitional decay between polynomial and exponential. And I will come back to this little later. Finally, when gamma is negative, which corresponds to fast-growing potential, we have even more complex decay picture. So we have exponential decay when q bigger than 1, polynomial decay, which decay depends on alpha, gamma, and q, but doesn't see p when gamma is not very negative. And finally, when gamma is negative, we have a phenomenon that all the parameters of the equation somehow involved in the decay. So all alpha, gamma, q, and p could be detected through the decay rate of the ground states. So those are all a priori. In a way, you can see these results are as a priori. The results for the ground states. If you want to look for a ground states, and if you then you know already a priori where it makes sense to look for the ground states and what decay rate you can expect from this ground state.
So I just have one question. So in the lower picture here, so you say that decay, I mean on the right hand side, decay doesn't depend on p.
No.
So I mean, what happens in the asymptotic limit if p is very large? Because this is when p is large, right?
Peak here could yes, peak could be sorry. P could be any large number. It just doesn't see p.
Right.
But here, this is what is expected. Here it doesn't see anything. Here it see
Right.
only gamma. Here, this case where everything is governed just by linear, you should see this like this. Here in this range, everything is governed by the elliptic operator on the left, by the Schrödinger operator on the left. Here in this range, our non-local Choquard starts to play a role. but here only partially, so here there is localization. This term decays at the same rate minus n minus alpha at infinity. So P is invisible. P is smoothed out completely by convolution. But here in this regime, somehow both P and Q are visible. So the smoothing out doesn't work. This becomes strong enough to be visible. Again, I will come back to a little bit to this phenomenon later. So this is what happens in the physical case. I will look at physical case dimension 3, P equals 2. Variational case, I will leave just one parameter free. This is gamma. So I will leave gamma as a potential. And this equation, or rather inequality, has a super solution if and only if gamma is less or equal than 1. And this is unexpected because anybody coming from local equations, from a local semilinear elliptic PDE theory, would expect threshold 2, gamma equal 2 here for existence and non-existence. But this is 1 because of competition between this convolution term and the potential, Schrödinger potential here. And the decay is governed by this rather complex formula. This is what happens here on this horizontal red line. So this is a little bit of explanation where this formula comes from. This is precisely asymptotic of minimal positive solution of green function of the Schrödinger equation. This is my original equation on the left-hand side. And this is what happens with the convolution term. So convolution term at infinity decays like m divided by x, but the m depends on the mass of u. M is self-governed by the super solution u we are looking at. And if you may wonder what happens with this integral expression, in fact, depending on the set of parameters for different gamma, we get longer and longer tails of corrections to u. So we have longer and longer. You can think of this as a Laurent expansion, or the sort of Laurent expansion, which could be finite, but could be arbitrarily long when gamma becomes close to 1. So asymptotics here is very complex. So now I want to talk, I have actually a short time left to talk about ground state. So what happens, now we are back to LEAP original prototype, but also I will recall the results for the local prototype equation when we don't have Riesz convolution here. It's a local Schrödinger. This equation, it's very well known that it has unique positive radial ground state solution if and only if P belongs to this interval. This is what is known as critical Sobolev exponent, and the equation has to be superlinear, so power P has to be bigger than 2. This ground state decays exponentially, and the rate of decay is precisely like green function of Schrödinger operator on the left. This range is sharp. Equation has no finite energy solutions when P is outside this existence range. So what happens with our more general Choquard, and this generalizes Leib's result. So this equation has a positive ground state solution if and only if P belongs to this range. This is certain extension of critical Sobolev exponent adjusted to the presence of the Riesz potential. This exponent is new. It was 2 before. In this context, we have 2 double P in the equation. This would be 1, what would be expected. But in fact, this is not 1. We can't push P up to 1. We have to stop somewhere, and this is related to the Hardy-Littlewood-Sobolev inequality. Basically, you have to just drop out the Laplacian from the equation and to look at the corresponding Hardy-Littlewood-Sobolev inequality to see the nature of this exponent here. When P is bigger than 2, we have a traditional exponential decay as expected. When P equals to 2, we have this complex transitional decay, which I already discussed a couple of slides before. When P is less than 2, we have polynomial decay of the solutions. And again, this interval for the existence of finite energy solutions is sharp, and this follows from Pahajayev identity. Let me skip the proof. The proof is more or less standard ground state minimization plus Pahajayev identity. I will comment on the physical case because surprisingly for us we can add something new to the Leib's result of 77. So apparently in the physical case asymptotical part is new because this asymptotic correction was never observed before. So what one would expect, and in fact there were at least one paper mistakenly claiming that the rate of decay of this solution didn't have this red color correction. In fact, there is a correction, and this is self-reference correction here. E22 is just the energy of ground state itself. So ground state obtained as a constraint minimization. So there is energy level which correspond to the ground state, and this correction comes into the decay rate. And this is manifestation of non-local feature of the equation, because of course energy is a global quantity which depends mostly on the mass near the origin. Mass is more or less, it's fast decay, it's still exponential decay, so mass is concentrated near the origin, but it somehow affects what happens at infinity. This quantity, this minimal energy mathematically is not known and not quantified. It does exist as a positive number, but we are not aware of any estimates on this quantity. There were numerical estimates in the physical group in Oxford around Penrose, and if the estimates is transferred to this correction, then this will be very small correction to the decay. I was trying to ask several physicists, I know whether this is significant physically or no, and I received no answer, so I don't know. But this is rather unexpected, also fine correction to the decay. Interesting open question here is uniqueness. Uniqueness, so Lieb proved uniqueness of the radial ground state. Uniqueness here beyond physical case P equals 2, P different from 2 here is difficult, is unknown, and we try to think about it, and it looks like a very difficult problem. We simply have no ideas how to approach uniqueness here, although we kind of expect that ground state will be unique in this setting. So this is all probably what I can say. Let me just one word, but also complete set of results. Of course, from the physical point of view, oops, I think it's running out because of my time. From the physical point of view, most interesting case when we have small parameter in the equation, and we have complete set of results for the semi-classical solutions. It's back now. When we have this epsilon parameter in the equation here and here, and all previous results, all Liouville theorems and knowledge of ground state somehow involved in analysis, directly involved in the analysis of this equation. But I obviously have no time to give you any details on this, so I'll just stop here. Thank you for your attention. Thank you.